Hello everyone, welcome back. In one of our last videos, we demonstrated how to perform linear regression in R using the tidyverse packages. Today, we will learn how to perform linear regression using the statsmodels package in Python. Before we begin, let's take an overview on what we will be learning today. In this course, we will be learning how to use statsmodels in Python to perform linear regression. First, we will go over the concepts of linear regression. Then, we will learn how to perform simple linear regression and multiple linear regression on several datasets. We will end with learning the techniques to compare, evaluate, and select the best model and do some predictions. Let's get started. Let's start with the concepts of linear regression. I'm going to cover the main concepts here. If you want an in-depth explanation, please watch my other video where I demonstrate how to use R to perform linear regression. Although in that video I am using R, the overall concepts are the same. The link to the video is in the description. Linear regression modeling is used in causal inference and statistical data analysis, and nowadays in machine learning and training artificial intelligence. Let's look at a general modeling formula. In this formula, y is a function of x. Y is called a response variable and x is called an explanatory variable. Y is the variable you want to model and x is the variable you use to predict the values of y. F denotes a mathematical function that defines the relationship between y and x. F of x is called the signal. E or epsilon is the noise that represents the error in the model. In a perfect model, E or the error becomes 0. This is the most important concept in modeling. A good model has a high signal-to-noise ratio. Today we will be using the conifers data, which contains the height and girth of different types of conifer trees. You can find the link to the data in the description below. The pandas package is the most widely used data analysis package in Python. We will first import the pandas package as PD, then we will import the conifers data using the read_csv method. We will save it as conifers. We can then use the head method to print the first 6 lines of the data. The shape attribute prints the dimensions of the data. We can see that the data contains 9,500 observations in 3 columns. The conifers data contains 3 variables. Type, which contains the names of 4 different species of conifer trees, namely oak, maple, pine, and birch, their heights in feet, and their girths in feet. Looking at this data, we can ask the following question. Does height of a tree depend on its girth? Mathematically, we can ask, is the height of conifer trees a function of their girth? We can now classify our x and y variables. The response variable y becomes height and the explanatory variable x becomes girth. Before we start linear regression modeling, we need to do an exploratory data analysis. Exploratory data analysis, or EDA, can be typically divided into 3 steps. First, we want to understand our data. Second, we want to visualize our data using different types of plots. And third, we want to calculate some summary statistics of our data. These steps will give us a high-level information of our data. The first step is to understand the data. This step we have already completed previously. We have seen that the conifers data contains 3 variables: type, which contains the names of 4 different species of trees, their heights in feet, and their girths in feet. To visualize the numeric variable heights with a categorical variable type, we can do a box plot. To make a box plot, we will use the seaborn package. First, we have to import matplotlib and seaborn as PLT and SNS respectively. Inside the box plot method, we will add the conifers data along with the x variable type and the y variable height. On the right, we can see the box plot. The line inside the box represents the median value. As we can see, that the median value of height of birch trees are the highest and the median value of the oak trees are the lowest. Pause here and try to do the same for the girth variable. Here is the box plot for the girth variable. We have set the y variable here as girth. Another way to visualize numeric data is to use a histogram to look at the distribution of heights and girths. This can be done by using the histplot method in seaborn, where we set x to the numeric variable we are interested in. In this case, we are looking at the distribution of height and girth for all the trees. We see that the median height is around 10 feet. We can also see that there are very few trees with heights that are greater than 25 feet. Because the histogram is tailing towards the right, we can say that the height data is right skewed. Skewed data is problematic in modeling since the data is not distributed evenly. Since there are only few trees with heights over 25 feet, it will be hard to accurately predict the heights of medium to shorter trees, which represent most of the population. This is also true for the girth data, which is also right skewed as well. To fix it, we can log transform the x-axis scale. Log transformations can be easily done by using the log10 method from the numpy package. First, we import the numpy package as np. Then we individually log transform the heights and girths and add it to the conifers data as log10_height and log10_girth. Using the log transform data, we plot the histogram again. As you can see that after log transformation, the data looks like a normal distribution, which will help with accurate modeling. There are two things to remember. First, log transformation in this case makes the x-axis intervals multiplicative rather than additive. And second, axis transformation is not always helpful, so perform transformations with care. Now we will calculate the summary statistics such as mean, median, and standard deviation of the data. We will use the group by method to group our data by the type of tree and then use the aggregate function ag to calculate the mean, median, and standard deviation. Like we saw previously in the box plots, the mean heights of birch trees are the highest and that of the oak trees are the lowest. The standard deviation is a measure of how dispersed the data is in relation to the mean, and we can say that the heights of oak trees are clustered tightly around the mean compared to the heights of birch trees. Pause here and try to do the same for the girth variable. Before we start linear regression, let's revisit the modeling framework once more. We saw that when y is a function of x, y and x are response and explanatory variables respectively. The term fx refers to the signal and the term e or epsilon refers to the noise. In a perfect model, fx will be able to accurately predict the values of y given some values of x. In our case, height is the response variable and girth is the explanatory variable. To perform modeling, we need to know these values. What is not known is the signal fx and the noise epsilon or e. Using the values x and y, we want to find a function f hat as represented by the dash on top of f that captures the true function while ignoring epsilon or e. The fitted function f hat ideally should be able to accurately predict the values of y hat based on the values of x. In this case, if we know the value of girth of a tree, our fitted model should be able to accurately predict the height of the tree. Previously, we were looking at one variable at a time, but not the relationship. In modeling, we look at two or more variables simultaneously. One way to visualize the relationship between two numeric variables is by using a scatter plot that visualizes the correlation between two variables. We will be using the regplot method from the seaborn package to make a scatter and regression plot. The x and y arguments are set to log height and log girth values. Looking at the plot on the right, we see that there is a positive correlation between height and girth. We can also calculate the correlation using the core function, and we can see that the correlation score is 0.04, which indicates positive correlation between height and girth. This means that as girth increases, height also increases. Now, let's look at how we can perform simple linear regression using the statsmodels package in Python. In linear regression, the equation is always that of a straight line. As a result, our fitted function can be represented as beta 0 plus beta 1 times x, where beta 0 is the intercept and beta 1 is the slope of the line. Our final linear model equation thus becomes y hat equals to beta 0 plus beta 1 times x. Notice that the epsilon was removed because in the ideal world, the fitted function f hat should only capture the signal and eliminate all noise. To compute the linear regression of our data, we need to use the OLS function in the statsmodels package in Python. First, we need to import the package statsmodels.formula.api as SMF. Then we will call the OLS function that stands for ordinary least squares. OLS takes two arguments. The first argument is a formula where the response variable is written to the left of the tilde and the explanatory variable is written to the right. The data argument takes the data frame containing the variables. To fit the model, you can add the .fit method. Printing the models with the params attribute gives us the model's parameters. These are the two coefficients, the intercept and the slope of the straight line. The slope here is labeled as log10 underscore girth. The intercept is the point on the y-axis where x is equal to 0. Before I explain the relevance, we first need to back transform the heights and the girths since they were log transform values. For back transformation, we raise them to the power of 10 using the power function from the numpy package as shown here. The intercept is 10.99. While mathematically the intercept is relevant, in our case it is not. This is because it means that a tree with a girth 0 will have a height of about 11 feet, which is not possible. The slope, however, has a meaning. A slope of 1.84 means that for every unit increase in girth, there is a 1.84 feet increase in the height of trees on average. Now it's time to make some predictions. Let's say we went into the field and measured the girth of a conifer tree to be 0.8 feet. Can we predict its height? To predict its height, we need to use our models' intercept and slope. Remember, we had log transform both height and girth. So first, we need to log transform 0.8 using the log10 function from numpy. Then we will multiply its value with the slope of 0.26 and add the intercept of 1.04. Finally, we need to back transform by raising the value to the power of 10 by using the power function in numpy. The new predicted height is 10.34 feet. Let's say we went back to the same tree with a girth of 0.8 feet and measured its height to be 15.2 feet. We can see that our model prediction of 10.34 feet has underpredicted the tree height. It could also be possible that our model had overpredicted the tree heights. This is the concept of residuals. Residuals can either have a negative or a positive value. For each predicted response value, there is a residual. We can calculate the residual for each response value by simply subtracting the predicted value from the actual value. In this case, the predicted height value from the actual value is about 4.9 feet. Now let's say we want to perform multiple predictions. We can do this one by one simply by plugging the new values and coefficients in our equation, but that will be tedious and for thousands of data points it will be impossible. statsmodels has a handy function called predict to help us compute multiple responses from a model object and new data. Before predictions, we need to first organize the data in a pandas data frame. We can use the aRange function that specifies the girth range from 0.1 to 0.9 feet with a step of 0.1. Remember that the last value, 1, is not included in the data frame. Since we used log10 transform values in our model, we need to transform the girth values using the log10 function from numpy into a new variable called log10_girth. Remember to use the same variable names as the original. We save the new data frame as new_data. Now we can use the predict method on the new data to calculate the log10 heights. We will then back transform them to the heights in feet by raising them to the power of 10 to get the predicted heights. To make it easier to see all the data, we can add these predicted height values to the girth values of the new_data data frame. To do this, we will use the assign method from pandas as shown here. For model objects, there is a method called summary. Calling summary prints several key details of the model. First, we see the dependent variable log10_height that was used in our model. We also see some metrics on the performance of the model such as r², the importance of which we will discuss in the model evaluation section later. We also see the coefficients, intercept, and slope along with their p-values which refer to statistical significance. We can also extract the fitted and the residual values using the .fitted values and .resid attribute for our model object. The .fitted values attribute is a shortcut for taking the explanatory variable columns from the dataset and then feeding them into the predict method. The residuals, as I've mentioned before, are the difference between the predicted and the original values of the dataset. In the previous section, we used a numeric explanatory variable, which is the girth of the trees, in our model. In this part, we will look at how to use a categorical value in our model instead. Let's ask the following question. Does height of a tree depend on its type? In this case, our explanatory variable becomes type and the response variable becomes height. You will notice that the explanatory variable is not a numeric one, but a categorical one. Before we start linear regression, let's perform an exploratory data analysis. This step we have already completed before. We have seen that the conifers data contains 3 variables. Type, which contains the name of 4 different species of conifer trees, namely oak, maple, pine, and birch, their heights in feet, and their girths in feet. As you can see that the explanatory variable here is categorical instead of numeric. To visualize categorical data, we can use a faceted histogram. To make a faceted histogram in seaborn, we will call the method facetGrid and within it specify the data, which is conifers, the categorical variable type for the call argument, and to make a 2-column plot, we set the call_wrap argument to 2. Then we use the map function, inside of which we call the type of plot, in this case histplot, and the x argument, which is height of the trees. As expected, we see a right-skewed plot, which is not good for our modeling as we had explained previously. When we use the log10 transform values, we can see that the plot looks normally distributed, which we will be using in our linear regression. Now we do the same to visualize the girth variable. Now we will calculate the summary statistics such as mean, median, and standard deviation for the data. This is the same as before. We will use the group by and ag methods to compute these parameters. Now we run the OLS function. On the left, we have the response variable log10_height, and on the right, we have the explanatory variable type. We have set the data argument to conifers. Then we call the fit method on our model and save it to the conifer_model_2 variable. When we call the params attribute on the model object, we can see that it prints 4 coefficients. One of them is an intercept, and the rest are from the 3 different species of conifer trees. The coefficient of birch is missing. Interestingly, if we raise 1.28 to the power of 10, we get the mean height of birch trees. The coefficients of maple, oak, and pine are calculated relative to the birch tree. For example, if we subtract 0.306 from the intercept 1.28, we get the log 10 height of maple, and if we raise 0.996 to the power of 10, we get the mean height of maple trees. We can simplify this by appending +0 to the end of the categorical variable type. This specifies that all the coefficients should be relative to 0, and this makes the results easier to read. We can now raise the coefficients to the power of 10 to get the mean heights of different trees. One thing to note is that this works well for simple linear regression, but if you have multiple categorical explanatory variable, it might not be useful. With that, we come to an end of simple linear regression. Now we will look at how to model with one response and multiple explanatory variable. This type of linear regression is called multiple linear regression. Let's say we want to see whether the height of trees depend on both type and girth of the tree. In this case, the explanatory variables are type and girth, and the response variable is height. To run a multiple linear regression as before, we run the function OLS. In the formula, we specify log 10 underscore height on the left side and log 10 underscore girth plus type plus 0 on the right side. For the data argument, we use conifers. Then we call the method fit and save it in conifer underscore model underscore 3 variable. When we run the params attribute on the model object, we see that it returns 5 coefficients, one for the log 10 underscore height, and the rest are for the different types of conifer trees. To make predictions with our multiple linear regression model, we first need to format our data as a pandas data frame. The data frame this time contains both tree types and girths stored in type and girth underscore feet variable respectively. To make combinations of our data, we will use the itertools function from the itertools package. First, we import the itertools package and then use the itertools.product method to generate all combinations of type and girth into a pandas data frame. Then we log transform the girth variable since we use the log transform values in our model. And finally, we have saved this in our new data frame called new underscore data underscore 2. We can now use the predict function on the model object and provide the data frame with the new values. We can use assign method to add the predicted values to the existing data frame. Finally, the predicted log 10 values were back transformed into heights in feet. With that, we come to an end of how to perform multiple linear regression using stat models in Python. Now we move on to the final and the most interesting chapter in this course, where we will learn how to evaluate and select the best model for prediction. Let's look at the two models. The first one models the height of trees based on their girth, and the second one models the heights of the trees based on their type. The goal would be to select the best model. There are several parameters that can be used to select the best model in linear regression. We will look at some of these now. The first parameter is called the coefficient of determination, which is also called R-squared. It is a measure of how well a regression model fits its data. R-squared values range from 0 to 1, where 0 indicates no fit and 1 indicates a perfect fit. One thing to note is that for multiple linear regression models, we need to use the adjusted R-squared instead of R-squared. For simple linear regression, we want to use the R-squared value. I have explained this in detail in my other linear regression course in R, which is linked below. When we use the summary method on the model object, the R-squared and the adjusted R-squared values are printed. Since we are comparing two simple linear regressions, we will use the R-squared values. Looking at the R-squared values, we can see that the model that takes into account the type of the tree is a better model since it has higher R-squared value of 0.6 compared to the other one that takes into account the tree girths. Another measure of model accuracy is residual standard error, or sigma. It is a measure of how well the regression line fits the actual data points. It tells you, on average, how far off the model's predictions are from the observed values. The residual standard error takes all the residuals, squares them, and divides the number by the degrees of freedom, and then takes the square root. The smaller the residual standard error, the closer the data points are to the fitted regression line on average, meaning the smaller the residual standard error, the better the model fits the data. A higher residual standard error means that the data points are more spread out around the regression line. The units of residual standard error are the same as the units of the response variable. Therefore, in the conifer's data, the unit of residual standard error is feet. The summary method doesn't print the residual standard error. Instead, we can use another parameter called mean squared error to obtain the residual standard error for the model. Mean squared error can be obtained by using the attribute called MSE_resid. Since this is a squared value, we can take the square root of mean squared error to obtain the residual standard error. We use the square root function from numpy to calculate the residual standard error for each model, and we see that the residual standard error value of the model that takes into account the type of tree is better since it has a lower value of 0.18 compared to the other one that takes into account the tree girths. Instead of looking at values or numbers, we can generate some plots that will help us visualize and quantify our model. Before we make these plots to visualize model efficiency, let's take a look at these two models. On the top, we have used the OLS function to model a sample of pine trees, and on the bottom, we have done the same for oak trees. Looking at the R-squared and residual standard error values, we can say that the oak model is better compared to the pine model. Both the sample datasets are linked in the description below. Now, let's make some plots to visualize and compare these models. If a linear regression model is a good fit, then the residuals are approximately normally distributed with a mean of 0. To help us visualize this, we can make a residuals versus fitted plot. To make this plot, we can use the residplot method from seaborn package, which we had imported previously as SNS. The lowest is set to true, which draws the red trend line. If residuals met the assumption that they are normally distributed with a mean of 0, then the red trend line should closely follow the y=0 line on the plot. When we compare both oak and pine data, we see that the oak data closely follows the y=0 line, thus making it a better data for modeling. The second plot type is called a QQ plot. It can be produced by first importing QQplot from statsmodels.api package and then using the QQplot function with the data argument set to model residuals, which can be accessed by using the .resid attribute on the model object. Interpreting this plot is easy. If the points follow the diagonal straight line, they are normally distributed. If not, they aren't. Here, most of the oak model follows the diagonal line closely compared to the pine model. If you look even closer at the pine model QQ plot, you'll see that the points deviate from the diagonal line towards the lower end and the higher end. This means that a model is a particularly poor fit for the longer and shorter height pine trees. Before moving to the final part of the lesson, let's understand outliers. An outlier is a data point in the dataset that is significantly different from other values. Outliers can be much larger or much smaller than the majority of the data points. Since their values are significantly different, they can have a huge impact on the model. The points in this box plot shown are the outliers. To understand outliers better, we have added a small sample of the birch data from the conifer dataset. The link to this data is in the description below. Let's import the data first by using the read_csv function and draw a regression line using the regplot function from the seaborn package. When we look at the scatter plot of the data, we can see that there are a few weird points. These are the outliers for this data. There are two kinds of outliers. The first kind of outlier is when you have explanatory variables that are extreme. In simple linear regression models, they are quite easy to find and visualize. You can see that there are two trees, one with a bigger girth and the other one has a smaller girth. These type of extreme explanatory values can be quantified using a parameter called leverage. The second kind of outlier is when it lies far from model predictions. Here we can see that there is a really short and thick tree. These type of values which lie far from the model predictions can be quantified using a parameter called influence. Leverage and influence along with other metrics can be retrieved by calling the get_influence method on the fitted model and then calling the summary_frame method. For historical reasons, leverage is also described as hat values. The values of leverage are stored in the hat_diag column of the summary frame. We can add the leverage values to the Birch data frame under the leverage column. When we arrange the leverage values in descending order, we can see that the top two values correspond to the birch trees with extreme girths. We can find the most influential trees by arranging the rows by descending Cook's distance values. Here you can see the two data points that had large residuals. Influence measures how much an observation impacts the estimated coefficients and the fitted values of the regression model. To see how influence works, let's remove the most influential birch tree. Then we draw the usual regression line in red, but add another regression line in green using the dataset without that unusual tree. Now we can see that the slope of the line has completely changed just by having one less data point. To summarize, before performing any kind of linear regression on your data, do an EDA or exploratory data analysis, then run the OLS function on your data, then evaluate model parameters, and finally use the best models to do your predictions. This brings to an end of this course on linear regression in Python using stat models. I hope you have learned something new today. If you loved this video, please like and subscribe to my channel. It helps me a lot. Thank you.